So let's look at half-lives. Again, not the video game. First thing we need to be aware of is radioisotopes decay and they form new elements. I can't emphasize how weird this was to scientists. We realized this at the turn of the last century, right around the 1900s. Up until then, we thought the periodic table was fixed and uniform, and it was a revelation to realize, oh my goodness, one element can spontaneously turn into another element through radioactive decay. But here's the important thing we're talking about today. Different isotopes decay at different rates. And by measuring how much of one type of isotope there is compared to another, we can make a pretty accurate guess is the wrong word, estimation is a better word, of how old something is. Some decay very fast. There are isotopes that decay in trillionths of a second. We don't use those for radioactive carbon dating because they're just not around. And some very, very slow. And here's our word of the day. To talk about their rate of decay, we talk about the half-life. What do we mean by half-life? That's how long it takes for half of the material to decay. It's half-life. So if 50% of a material is left, we measure how long that takes to occur. That's the half-life. And then another half-life, 25% of the material will be left. Another half-life, 25 divided by 2, 12.5% of the material will be left. Another half-life, whatever 12.5 divided by 2 is. That's why I said get your calculators. So this is the time it takes. Can you read okay back there, or do I need to make it a little larger? Yep. For 1/2. What's 1/2 as a percentage? That's as a fraction. What is it as a... Okay, so 50%, you may see it written that way, 50%. Faster decay. Shorter half-life. If you look at your green sheet, at the bottom here, I've got some common half-lives of some elements. So if you take a quick peek at it, what's the half-life of carbon-14? You don't need to memorize it, okay? So carbon-14 is, we can use that to date objects that aren't that old. It's good to dating about 60,000 years or less. What's the half-life of uranium-235? 110 million years, and it goes all the way up to the half-life of rubidium-87. It would take 47 billion years. If you had 1 gram of rubidium-87, it would take 47 billion years for that to decay to half a gram. Okay? But we can measure that, and again, all of these give us what we call geological clocks. This is how we can figure out how old rocks are or how old organic samples are. Back to the notes. So one of the more interesting one is carbon-14, C14. It is the radioactive isotope of carbon. Normally carbon has a mass of 12. That's the one that's on your periodic table. That's the stable one. Carbon-14 has picked up a couple of extra neutrons. How? Typically it happens in the atmosphere with cosmic rays bombarding the Earth. There's stuff going on up there. But what that means is out of every chunk of carbon, a certain percentage of it is carbon-14. And because plants are made of carbon, and because trees are made of carbon, and because we are mostly made of carbon, this allows us to look at objects that were once living and are now dead and estimate pretty accurately how old they are. This is how we figure out, for example, if we find a woolly mammoth carcass that's frozen in the Siberian tundra and we want to know when it died, carbon-14 dating. This is how we figured out how old King Tut's tomb was, carbon-14 dating. Okay? So while alive, organisms ingest, that's a fancy word for take in, and lose carbon. We're taking it in and we're losing it. And so while we're alive, I'll take your question in a second, Raf. We keep the same ratio of carbon-12 to carbon-14. Which one? the top. There, can I do that? Question. Yep, question.
If I recall correctly, a tundra would be a huge snowy place. Right?
Yep. Typically frozen year-round.
Yeah.
And so, especially in Siberia, as either the tundra is thawing or as we're doing mining or digging, we do find well-preserved woolly mammoth, sometimes skeletons, but sometimes the actual carcass, the actual dead body. And so this is how we've been able to get woolly mammoth DNA from hair and things like that. We found woolly mammoth babies that are frozen as well. And so this is how we know that woolly mammoths were still around when humans were around. We have woolly mammoths that are less than, when we do the carbon-14 dating, we can date them to about 8,000 or 10,000 years ago, and we know people were around then. We also have legends, we have oral tales that have been passed down from tribe to tribe of this furry elephant-looking thing with the long nose, so we also know that people saw them, but we can also prove it, not just from the legends and the myths.
So, elephant wannabe.
Part of the same family that diverged up the tree.
The elephant is probably the mammoth wannabe. Like, if anything was a wolf, the elephant wannabe.
Wait.
But there's a limitation with carbon-14 dating. It can't date objects that are still living. Once an object dies, or if it's a tree and you cut it down and use it to make something out of the wood, the carbon-14 continues to decay. So the longer something has been dead, the less carbon-14 there is. So this can be used to measure how old something is, like King Tut. Okay, they would have taken a very, very small either skin sample or fingernail sample or a sample from the hair. But the limitation with carbon-14, it can only be used to date objects that were once alive. Doesn't work for rocks. But we have other ones that work great for rocks. Okay. Yes, there is a song. But what I really want you to realize is carbon-14 dating is pretty accurate. We do have a pretty good indication of how old something is. So for example, if an archaeologist digs up or uncovers a cave where it looks like people have lived many thousands of years ago, but there's no remnants of the people, and there's rocks around, how can we figure out how long ago people were there? Hey, if we find some campfire ash, the campfire ash was once wood, we can carbon-14 date that, and it's a pretty good bet that the campfire was built by the people that were there. We can't be certain. It's possible several thousand years later someone built a campfire in there and then left. And this is why you're going to hear me often say the word estimate instead of exactly how old something is, because we weren't there. But you do enough of those carbon-14 datings, and you can be pretty sure we're bang on. There's common isotope pairs, isotopes that undergo radioactive decay. The isotope we start with, we call the parent isotope. And then when we finally get to a stable product, we call that the daughter isotope. And again, if you look at your green sheet, that chart shows you a bunch of common parent-daughter pairs. Carbon-14 decays into daughter nitrogen-14. Uranium-235 decays into lead-207. And once it gets to lead-207, it's pretty stable. Radium-87 decays into strontium-87. So I wrote here in your notes, uranium-235, which we would write as U-235 because we tend to abbreviate, decays into lead-207, which we would write as Pb-207. And I wrote here, see your reference sheet for more common pairs. I put some common ones here. You don't need to memorize them. They're there. You just need to know that they're there to go looking for them. Put your pencils down, look up. Here's where you're going to need a calculator, and here's where Ava's going to put her phone away. Here's where it's going to get a bit tricky. I'm going to do the mathematical method with you, and then what I've done instead is I've printed up a bunch of graphs and charts that we can just read from, but I do want to show you because somebody asked, how does this work? So half-life means we're going to be dividing by 2 an awful lot on our calculator. Suppose you have 120 grams of substance X. It's radioactive. I'm making this substance up, but it's got a half-life, shh, quiet please. It's got a half-life of 8 years. So after 8 years, that would be 1 half-life. After 16 years, how many half-lives would that be? 2? 24 years? 3? And you can continue the pattern if you need to, but you spotted the pattern? So let's suppose we start with 120 grams. After 8 years, how much would be left?
None.
Nope. Half of it's decaying.
Oh.
So the opposite of 240, other direction. I heard it there. 60. So that means if I knew this substance had a half-life of 8 years and I knew I'd started with 120 grams and there was now 60 grams left, I could say this is 8 years old. After 2 half-lives, how much would be left? After 24 years, 3 half-lives, how much will be left? After 32 years, 4 half-lives, 15 divided by 2, 7.5, and I start to use a calculator after that, but most of them I can divide by 2 initially in my head. What about if we wanted to write this as a fraction? Well, we would say you have 1/2 remaining, then 1/4 remaining, then 1/8 remaining, then 1/16, then 1/32, 32 times 2, 64th. It's the powers of 2 on the bottom there as well. I'm probably not going to be doing the fraction much, but I will often ask you a percentage. Whenever I ask you a percentage, Cassandra, assume we started with 100%, the original amount. So after 8 years, what percent would be left if we start with 100%? 50. And in fact, the graphs that I gave you on the y-axis, I put percentages because that was just easier to use. You'll get a graph in just a few minutes. After 16 years, how much would be left? 25%. After 24 years, how much would be left? 12.5%. Now, it's important to know that stuff isn't vanishing. It's decaying. It's transforming into the daughter isotope. So at the beginning, there would be 0% of the daughter isotope. After 8 years, it would be a 50-50 split. After 16 years, if 25% is the parent, what percent has turned into the daughter isotope? 75. And so that actually gives us 2 ways to date objects. We can either measure the amount of the parent isotope left or the amount of the daughter isotope left. We typically do whichever one is easier to collect and measure because some of these are pretty tough to measure. Oh, and then we would have 87.5% left. Okay? So one way to do this with a calculator is to draw a big chart. I'm lazy. I'll show you a shorter way that's still organized in a few minutes. But we can now answer the questions. A says, after 8 years, how many grams of X do we have left? 8 years, 60. After 16 years, how many grams of element F do we have left? Element X do we have left? 30. After 16 years, what fraction of the parent isotope is left? 1/4. After 16 years, what percent is left? Now 25. Yep. After 24 years, how much parent isotope material is there in grams? Looks like 15 grams left. So how many grams is now daughter material if we started with 120? I don't know. How would you figure it out? What did we start with? 120. We have 15 grams. That's the parent. How'd you figure that out? Tell me out loud. What'd you do? 120 take away. Yeah. And again, if you can do it in your head, great. Or you got a calculator if the numbers are yucky. I can't always make the numbers nice. This one I made up an element, and so I made the numbers nice. But in real life, the numbers are just yuckier. Sorry. So 105 grams. Next page. Example 2. Turn the page. Give me a few more minutes, yep. Duicium, this is another element I made up. It's a mysterious radioactive substance. It's got a half-life of 7 minutes, so it decays fairly quickly. Suppose we start with 60 grams of duicium, and then there's a bunch of questions. I don't want to do a big chart, so here is my minimal amount of writing, maximum organization. I do something like this. How much did we start with? Read careful, loud and proud. I write that down. And then what I do is I do some arrows. Each one of these little loopy arrows is a half-life. I draw 3 or 4, and then if I need to add more, I will. So this is 1 half-life, 2 half-lives, 3 half-lives, 4, and if I need to go further, I will. Okay? And I can fill in how much is left. If I start with 60 after 1 half-life, how much is left? After 2 half-lives, how much is left? After 3 half-lives, how much is left? And after 4 half-lives, how much is left? 3.75. Someone double check me. 7.5 divided by 2 is what? Got a calculator, check it for me. 7.5 divided by 2?
Divided is the red one, right?
Yeah. I don't know what you're calculating. Is it 3.75? Hey, I can do math in my head still. If I need to go further, can I? Yes. Will I? Only if I need to. So I usually just draw 2 or 3. And then underneath that, I also put, instead of half-lives, the amount of time. How many minutes is 1 half-life? I'll put a 7 there. 2 half-lives, that must be 14 minutes grand total. 3 half-lives, that must be 21 minutes grand total. 4 half-lives, how many minutes? Okay. Now, normally I'll only draw as much of that as I need to, but this is my setup. I think that's way less work than trying to do a big chart. And now I can answer the questions. After 14 minutes, how many grams are left? Right? 15.
That's me. One human.
After 28 minutes, how many grams are left?
3.75.
Yep.
That is a small human.
Oh, after 28 minutes then, how many grams of the daughter isotope are left? Well, how many grams did I start with? 60. How much is left of the parent? 3.75. How could I figure out how much is turned into the daughter from that? So this is, again, why you have a calculator. Can someone on their calculator go 60 minus 3.75? 56.25?
I didn't do that with the calculator. I did it in my brain.
There you go.
Isn't that crazy?
Wait, divide or multiply?
Subtract.
Oh, 56 minus.
D. How many minutes are we talking about now in D? Okay, I guess I need to extend this by 1, or maybe I can just do it on my calculator, because 35 minutes would be just 1 more half-life. So 3.75 divided by 2. I got to extend it 1 more to get to 35 minutes. What is 3.75 divided by 2? Raphael?
1.875.
Is that right?
Yep.
So 1.875 grams. Oh, but they wanted this as a percentage. How do I make that a percentage? No,
Back
easy.
in time.
Start with your calculator. This is where everybody wants to get their calculator out. Here's my big fancy graphing calculator. We're always going to start with 100%, all of it. So everybody type in 100.
100.
And then divide by 2. That's the first half-life, 50. How many half-lives are we going to need to do to get to 35 minutes? 5. So divide by 2 again. That's the second half-life. Divide by 2 again. Third half-life. Divide by 2 again.
Button.
I don't know on your calculator which one divide is.
Yeah, that's third button.
And then divide by 2 one more time. What percent is left? Now, if your calculator is giving it to you as a fraction, I can show you how to change that to a decimal. You got either an S to D. If you're borrowing one of my calculators, there you put it. Who's borrowed calculator is giving the answer as a fraction? You. Okay. So what you're going to press when you're done is change. And again, there's decimal. Okay. Second, do you have a question about when you're giving it to you as a fraction? Yes?
No.
Oh, you're good.
I have to use the lock number first. I asked for.
Okay, so Sadie, hustle back, and then when Sadie gets
I
back,
asked before some of we're done enough.
5 minutes later, you
No,
can
you're
go
done.
home now.
you have one? I thought I asked who needed one. Did I not give you one?
Okay, yeah, fine. Can I have one as well? Okay. Like, so okay, do it.
Okay, I can't give you a basic one. You're gonna get a fancy one.
Am I still there?
Battery died. Oh wait, I got this one. This is not fancy schmancy. Battery's dead. Oh no, this one works. One for you. You're actually reaching your hand out. Battery's dead. Battery's dead. Hang on a second, Raph. Oh, somebody wrote some cheat notes in here thinking they were clever. I would have thought. Raphael, you had a question?
You know, that'd be very strange.
What?
Doing math questions while using your calculator upside down.
Yeah, but wouldn't work very well. So, back to here. Sorry for those of you at YouTube for the pause. What percent is left? So, to find the percent, start with 100 and just keep dividing by 2. We said that this was, on my calculator, 3.125%. I divided by the 100 by 2 5 times, 5 half-lives. What percent of the daughter isotope is left? Well, if I started with 100% and 3.125% is the parent, I guess 96.875% has turned into the daughter.
Wait.
Yep.
Not right.
100 minus 3.125, 100% minus 3.125% gives us 96.875%. Now, the calculator method is a bit of a pain. I'm going to do one more with the calculator, and then I'll show you what I think is a little easier way to do it. But we'll start with calculators. So example 3, one more. Suppose a substance has a half-life of 4 hours. If we start with 80 grams, what will be left after 1 day, 24 hours? We need to figure out how many half-lives that is. If one half-life is 4 hours, how many half-lives in 24 hours? Acacia, 6. So what we need to realize is if we go 24 divided by 4, that's 6 half-lives. I'll go HL as my abbrev for half-lives. So how many times am I going to divide by 2? 6 times. So it's going to be 80 divided by 2, that's once, twice, 3, 4, 5, 6. On my calculator, I'll count 80 divided by 2 once, twice, 3, 4, 5, 6. And you can make a little list or you can count on your fingers or whatever. I'm not going to ask you to do like 40 half-lives, something like that. I'm going to ask you to do 3 or 4 or 5 or 6 at the most. Okay? How much is left, Mesa? 1.25 grams.
I like how you asked the little question.
Pardon me?
I like how you asked the little question.
Yes. And there is. Pause. So can you all look at the piece of paper, the 4 graphs that I just gave you? These are called decay curves. Now, unfortunately, for those of you in the back corner, for me to get this graph on one screen means it's going to be a little small for you to read the numbers, but you have it in front of you. Can you look at the first page? This is the half-life of carbon-14. Okay? And then kind of look up. I'm going to use the little laser pointer thingy here. On the y-axis, this is the percentage remaining. So can all of you go up along the y-axis to where it says 40% right there? If you read across and then you drop down, that'll tell you approximately how many thousand years old this is. So we're going to do one together. I'm going to pause the video for a few minutes. We've been talking about decay curves, so if you want to go into your notes, I gave you a smaller version of a decay curve that I can fit on one screen. So I said, is there an easier way to do this? Yeah, we can use a decay curve. We can use a decay curve. And Kaylin, on the y-axis, we put the percentage. I can't go up by ones and fit it all on one piece of paper, so you'll have to kind of use the scale to figure out roughly where we are if you want to find like 30% or 20% or something like that. But then what you do is you read across until you hit the curve, and then you drop down, and that tells you approximately how old the substance is. And again, on the bottom axis, on the x-axis, again, Jaden, I can't go up by ones. You'll kind of have to look at where the numbers are, and oh, I'm halfway between 8 and 10. That's a 9. I'm between 8 and 10, but I'm closer to the 8. Probably 8.5 or 8.2, best guess. And I'll mark a range of values when you're looking at my answer key. As long as you're close to me, you're good. So here is a mystery element, element X. What's its half-life? Well, if I go to 50%, read across and drop down, what's its half-life in billions of years? 1.3 billion years. Okay. Yeah, we're back to our notes. Yeah. Okay. Yeah. Okay. Ava, my angel, look up. B says, what percent is left after 3.9 billion years? So I can either give you the percent, read across, drop down, or I can give you the time. So the time, 3.9 billion years is right here. Read up and then read across. I would take 15. It looks to me like it's half of 25. Probably 12.5 is the most accurate answer. But again, because we're estimating from the graph, I'll take a range of values. I would not take 24, and I would not take 5. That would be too far off. Okay? I would take 12.5, and I'm going to put 12.5. 12.5%. What percent of the daughter isotope would be present after 3.9 billion years?
It's a top.
Casey.
It's a top.
Good. Don't write this down, but someone usually asks, don't add this to your graph. The daughter graph would actually look like this. That would be the daughter increasing. 87.5%. By the way, if it's got a half-life of 1.3 billion years, from your green sheet, what element is this probably? Sorry? Potassium 40?
This is why we have the gamma.
K40? Okay. Next page. Shh. Quiet, please. So here's a decay curve for carbon-14. I also gave you a big one on the sheet. So this shows the amount of carbon-14 that would remain in a sample 30,000 years after the organism died. Can you see why carbon-14 dating doesn't work much past 50,000 years? Because 50,000 years over here, there will be so little left, it's just almost undetectable. So carbon-14 dating, good to about 50,000 years, it's useful, and it has to be a living object. Folks, I need to be quiet or I'll move you, okay? Put your pencils down and watch the screen.
Straight.